To begin this video, I'm going to already assume some knowledge of the JK flip-flop, its relevant symbols, preset and clear functions, binary numbers, and basic logic gates. If you need help with any of these, I have posted some great links in the description to get you started. In this video, I'm going to go through a binary counter setup using 4 JK flip-flops. For a binary counter, the flip-flops are set up in a way such that the output Q of each device is connected to the clock input of its neighbor. The JK inputs are left unconnected, which results in both being in a high state. If we remember our JK flip-flop truth table, we know that with both J and K inputs at high, the outputs Q and Q bar will toggle, and the output previously at Q will go to Q bar, and the output previously at Q bar will go to Q. This will make more sense once we get started. For every 2 toggles in the first device, 1 toggle will occur in the second device, and so on until the 4th device. A binary number is produced at each pulse, with the last flip-flop containing the most significant bit. In this counter, there are also preset and clear buttons. The preset button is left unconnected and left in a high state, but it is only triggered on a low, designated by the circles above it. Therefore, in this circuit, the preset will never be triggered. The clear function will also be triggered on a low, but its input will depend on the output of the NAND gate. The NAND gate is connected to the Q outputs of B and C and the Q bar output of D. In order to achieve a low state to activate the clear, the B and C outputs must be high, while the D output must be low. Suppose this is our clock input. The absence of a circle in front of the clock at the first flip-flop indicates that the A output will flip on the positive edge of the clock pulse. The second, third, and 4th flip-flops, however, do have the circle in front of the clock and will flip on the negative edge of the previous device. If every output starts in the low state, our schematic will look like this. Now we can implement our clear function. If we remember our NAND gate setup, we need B and C high and D low to activate the clear. This occurs here. Therefore, all outputs will be zeroed until the next positive clock pulse, at which point A will toggle and the pattern continues. Now, remembering that the D output is the most significant bit, we can create the binary numbers at each pulse. We can see that this counter counts from 0 to 5 and then resets and counts again. This is what we would call a modulus 6 or mod 6 counter because we have 6 stable states at which we have an output number before resetting. This concludes my video explanation of binary counters. If you have any questions, please comment below and I'll do my best to answer. Thank you for watching.